Okay, so welcome to the 14th video in the Discrete Structures series, and this video is going to be all about the Euclidean algorithm, and this is an algorithm used to compute the GCD of two numbers. Then we'll be looking into the Bezout's theorem and see what we call Bezout's coefficients. And then we'll look into the problem of finding the Bezout's coefficients for two given numbers, and that will involve the extended Euclidean algorithm. And we will be looking at numeric examples for the Euclidean as well as the extended Euclidean algorithm along the way. Okay, so that is the overview. And before I jump into our first topic of Euclidean algorithm, I want to mention a few applications. So this is used, for example, in finding the modular multiplicative inverse of a number. And that is used directly by the RSA algorithm, also called the public key encryption algorithm. And pretty much all of modern security is based on these algorithms. Okay, that aside, let's have a look at the Euclidean algorithm first. So let me note Euclidean algorithm. So the Euclidean algorithm is used to compute the GCD of two numbers, as we talked about earlier, and GCD stands for Greatest Common Divisor. So the greatest common divisor for any two numbers is the biggest number that divides both of them. For example, if I were to take two numbers, let's say 84 and 30 for an example, and let us begin with the traditional way of doing this, the prime factorization method. So I would write 30 is equals 2 times, and that leaves me with a 15, and that is 3 times 5. And similarly, 84 would be 2 squared times 3 times 7. And then I would say that the GCD is the minimum of all the powers. So that would give me 2 to the power 1. So I take 1 from here times 3 to the power 1. The minimum is 1 in this case. And what happens to 5? We discussed this in our earlier video. So I have a 5 to the power 0 here and 5 to the power 1 here. So taking the minimum would lead me to a 0. And therefore I would not multiply 5 to the power 0, right? That would just be a 1. And so for 7, also 1. And this would give me a GCD of 6. And now let's see how the Euclidean algorithm does this. And before we formalize this concept, let's imagine this configuration. I'm trying to make a point here. So I'll put my two numbers 84 and 30 inside my box. So 30 here and 84 anywhere. And this time we know in advance that GCD is 6. So let's also have a look at this and see how things work around here. So let me do something arbitrary. This will make sense later. So let me take the difference of 84 and 30. Okay. And this difference would be 54. And let me make a claim here. I can put this 54 inside the box and the GCD of these three numbers would still remain 6. So it is not just that the GCD of 30 and 84 is 6, but having 54 also doesn't change anything. But what is the advantage of doing this? See, now I can work with smaller numbers. I can just take 30 and 54 and repeat the same process. So if I were to take the difference of 54 and 30 now, this would give me 24. And then I could put 24 into the list again. And now what smaller numbers would you choose? 30 and 24, right? And that would give a difference of 6. And then the smallest numbers are 24 and 6. So let me keep going on and see where it takes me. So I get 18, I put it here. Again, 18 and 6 are the lowest numbers. So I could take any two numbers, right? But I choose to take the lowest ones because that simplifies me towards the GCD. So the next number that I get is 18 minus 6 is 12. And 12 minus 6 is 6. And finally 6 minus 6 is 0. So whenever I get 0, the two numbers that are subtracted were equal. And that is in fact the GCD. Okay, so that is the core of the Euclidean algorithm. There is just one optimization to make here, but once we do that, this is gonna be done. So to take this point home, let us do this problem formally. Okay, so let me get a little bit of space here. So I need to calculate the GCD of 30 and 84. And I mentioned earlier that there was one optimization to be made here. So in the previous demonstration, we took 84 and we just subtracted 30. Okay. But what I can do to optimize this is I can subtract any multiple of 30. Because if subtracting 30 once is allowed and the resulting number produces the same GCD, so does subtracting it 2 times and 3 times and any number of times for that matter. So I can make it better by just not subtracting 30 but 30 times 2. Okay, so I could write 84 minus 30 times 2 and that would still be a new number that I could work with. So this is 84 minus 60, that is 24. And therefore, now I'm looking at the GCD of 30, 24 and 84. The two smaller numbers that I pick would be 30 and 24. And you see this got me to the result much quicker. Previously, I kept subtracting multiple times. Okay, so let's formalize this like I said. So applying the Euclidean algorithm. So you begin by writing 84 and you subtract as many 30s as you can, right? So that would be 30 times 2. That's the best I can do. And then I have a remaining 24. And I don't want you to care about this expression, but think about the logic. Now I have my numbers 30 and 24 and that's all I need. So I want to write the following expression. 30 equals 24 times 1 plus 6, right? So my domain now has 24 and 6, and I could write 24 equals 6 times 4. And you see, this is the stage that got me no remainder. So whenever there's no remainder, you look the second to last number and that is your GCD. Okay, and this number is also the same as this multiplier. So all you need to do to get the GCD by Euclidean algorithm is to show these steps and to conclude that the GCD of these two numbers, let's say 30 and 84 in this case, is equal to 6. And let me tell you, there is the extended Euclidean algorithm, but it follows the same steps up to this point. Okay, so you have to do this anyway, and there is an additional step that you need to do in order to extend the Euclidean algorithm. So we will come back to the same problem later when we need to solve the extended algorithm. But before the extended algorithm can be discussed, we need to learn about two requisites, and these are the Bezout's theorem, and we do not need the proof for this. And this is quite simple. Let me put the statement forward. So the GCD of any two numbers a and b can be expressed as the linear combination of those numbers. So I could say this is a, b, okay, and multiply this with, let's say, k1, multiply this with k2, and you are allowed to add. And doing this is called taking a linear combination. And the theorem suggests that for any two numbers a and b, you would always be able to find these coefficients k1 and k2. So for our previous example, 6 was the GCD of 84 and 30. So that means I can write something times 84 plus something times 30 would be equal to 6. That is all it is telling me. And then for our case, if I put a 3 here and let's say a minus 1 here, because k1 and k2 again can be integers, k1, k2 belong to J. You see, using the coefficients minus 1 and 3, I'm able to equalize this equation. So that is all the theorem suggests, that the GCD can be expressed as a linear combination and those coefficients k1 and k2 can be found. Okay, and these coefficients have a special name. They are called Bezout's coefficients. So the proof for this exists, but we'll not be looking into the proof here, but we'll definitely be looking into the task of finding these Bezout's coefficients for a given set of numbers, and that is the extension of the Euclidean algorithm. So the extended Euclidean algorithm. Okay, and let me put the extended version of the previous question here. So compute the GCD of 84 and 30 and express it as a linear combination of 84 and 30. So the first part is something that we already did earlier and it comes from the Euclidean algorithm. So let me just speed write it here. Okay, so this part is the Euclidean algorithm that we borrowed from earlier. And then the question asks me to express this GCD 6 as a combination of 84 and 30. And we looked at how that was possible earlier. So I'm looking for my coefficients 3 and a minus 1 here. Okay, so we do this process by reverse tracking what we did in the Euclidean algorithm. So we did this from top to bottom. Now we need to recollect items from bottom to top, each time expressing 6 as a linear combination of higher and higher numbers until we reach 84 and 30. So this last equation that didn't leave a remainder is not useful. So we always start with the second to last equation. And I want to express 6 as a combination. So I start by writing 6 equals 30 minus 24 times 1. Okay. And in this step, I have expressed 6 as a linear combination of 30 and 24. But I'm being asked to be able to express as a combination of 84 and 30 instead. And that will give me a hint of what I need to substitute. I need to find a substitution for 24. And I always look into one equation above the previous one in order to do that. And this tells me that 24 equals 84 minus 30 into 2. Okay. So I could say 30 minus, put a substitution for 24. That would be equal to 84 minus 30 into 2 from this equation. And then into a 1. That doesn't even matter. And do not confuse by looking at all the numbers. Your target numbers here are 84 and 30. So we'll try to group them together. I get minus 1 times 84. And see, this minus and this minus will multiply to give a plus. So here are 2 30s and here is 1. So I have total of 3 30s. Okay. And this is my final result. So in this process of tracking back, you always want to start with the second to last division and you want to go all the way to the top. This involved 3 steps. So tracking back 3 steps got me back to my original GCD. If this would have involved, let's say, 5 steps to get down, you would have needed to make 5 substitutions to be able to get back. So this extension of the Euclidean algorithm in order to compute the Bezout's coefficients is called the extended Euclidean algorithm. Okay, So that concludes the content for this video. In the next video, we'll be looking into the ideas of integers and algorithms for addition, multiplication, division, and the remainder algorithm. So I will see you guys in the next one. You guys have a good day. Bye.